A very warm welcome to XL Catlin Arctic Live here from the UK Arctic Research Station in Ny-Ålesund, Svalbard. I laugh slightly, a warm welcome, but a slightly horrible day. It's here beginning of May and we have rain in the Arctic. There was a lot of flurries of snow overnight and high winds, but that's calmed off and we're left with this sort of slightly soggy morning. But welcome. Anyway, I'm very excited to have, I think we have 40 schools or more registered for this morning's session looking at ocean acidification. We have schools from the UK, from China, from Spain, Romania, Greece, Kenya, Nigeria, India and Russia. So welcome one and all. Please do find us on the YouTube live page and send in your comments, and there's a live chat there so we can see what you're up to and your thoughts and your questions. This morning we are looking at ocean acidification. We've talked quite a lot about ocean acidification over the past live broadcasts, and it's one of the focuses of the science up here. And we've got a little activity for you, and I hope that some of you will be following that in classrooms where you are. So just to check that you have the items you need for this morning's live investigation. Hopefully you've got some water. This is just tap water. Very important that this will be much easier if you don't use seawater, this tap water. And if you live in an area with a particularly hard water, so there's a lot of calcium carbonate in it, you might want to find some way of maybe boiling the water. Oops, should have said that yesterday. But having previously boiled water to take some of the minerals out of it, that will make this much easier. So some water. You will need some vinegar. I'm trying not to get these two confused because bubbling through vinegar might be fairly disgusting. Some vinegar. You then need some calcium carbonate, so chalk or a seashell, like a mussel or oyster. A straw. Please try not to use single-use plastic straws. They're one of the sort of ways in which plastic gets into our ocean and harms marine life. So this is a metal straw, lovely reusable straw. So even if you do have this with us once, a plastic single-use straw, please think in the future about changing to more sustainable straws. And then as part of this, we need to measure the change in pH, and we'll come on to what pH means in a little bit. I have a pH meter, but you can use a range of different things to measure the change in pH. Natural indicators such as boiling up red cabbage or litmus papers or other items you might have in the school lab. So those are the things that we need for our investigation. So just in your classrooms now, make sure you've got everything ready. If you're doing this live investigation with us, we're going to start off by trying to replicate the process of ocean acidification with our little ocean here and adding carbon dioxide through this straw. So just to go through what we're looking at with ocean acidification is the process by which excess carbon dioxide in the atmosphere is being absorbed into the ocean and changing its pH. And pH is a measure of acidity. Now, what we're finding is that, for instance, the oceans behind me here and the Arctic are about 8.1. We'll probably find that the pH is lower here because we've got a lot of runoff, so melting glaciers, so water running off the glaciers. and fresh water with a pH of 7 or around 7, seawater 8, 8.1. Ocean acidification is, it sounds like if you look at the figures that it's not a big issue. So pre-industrial revolution, 1750, about 250 years ago, the pH of the oceans was about 8.2. So we've seen a 0.1 of a unit of pH decrease over those past 250 years. And 0.1 doesn't sound very much. 0.1 of a gram, not very much. But with pH, it's a logarithmic scale, meaning that 0.1% of a drop, 0.1 of a unit drop, sorry, represents a 30% increase in acidity over the past 250 years. Now we talk a lot about this process of ocean acidification, how adding carbon dioxide to the ocean results in a change in pH. So the first thing I need to know before I look at that change is what is the pH of my ocean to begin with. So wherever you are, let's just check online to see if we're all there. And just getting the live stream up now. Here we are. Before I blow into it, I'm going to use my pH meter just to test the tap water in Ny-Ålesund, where we are. Now, the water that we get is high pressure glacial runoff. So we're expecting a pH probably around 7. So I'm just going to take the buffering solution off the side here. Very careful not to spill this, as the water in the end here, the solution in the end here, keeps this probe at a calibrated level. Switch it on. And then put it into our water here. And we can see the pH going up here. If I show you, Ellie, who's behind the camera, might be able to tell me whether we're nearing 7 or not, or whether we're slightly below.
6.66, 67, 68, 69, 6.7, 7.1, 7.2, 7.3, 7.4.
Okay, so we're heading up towards 7, so luckily we're fairly on the money there. We're going to settle down. Do you think, Ellie, can you see that for me?
Yeah, it's 6.91. It's climbing towards 7.
Climbing towards 7, but slow. So we must be nearing the pH of the water here towards 7, just a little below. So wondering.
That's 7.
How we're doing. Yeah, 7. Look at that. Now carefully take this out. Go on here. Ooh. Turn it on here. Rest that down. And now for the next part, to acidify my tiny ocean. If you're doing this at school, take it in turns. Maybe if you're doing it in a group, each have your own straw for hygiene purposes. But please don't pass out by blowing through a straw too much in the classroom. Ellie has kindly volunteered this morning to do that for us here, whilst I talk through.
Hi everybody. I may regret this.
You're all mic'd up there.
Yeah. I'm really pleased that we've not got plastic straws. That's great.
I'm really pleased it's also not cold. So there's what could possibly go wrong using a metal straw in the Arctic.
If it were -40, we could use a bamboo or wooden straw instead, because that doesn't freeze tulips.
I forgot to bring my bamboo straw with me on this trip, I'm afraid. But
so you want me to blow into this?
Yeah, I think let's do that. Let's do collectively. If you have your experimental oceans ready, let's see how many students we can get doing this around the world, and we will go for 2 minutes.
Okay.
Probably not more than 30 seconds at a time for students. But Ellie, if you can do 2 minutes, that would be
2 minutes. Okay.
That would be fab.
Let's go.
Let's go. And so what's happening here, if you could, we've got the gentle bubbling going onto my side, is that there is, because of respiration, we have more carbon dioxide when we breathe out. So when we breathe, or when Ellie, thank you very much, breathes through the water, she's putting carbon dioxide through that. And so when we add carbon dioxide to water, very basically we get carbonic acid before that goes into different ions. It's sort of aqueous carbon dioxide and then carbonic acid. So after you're doing really well, you're not going to pass out yet. So we're coming up to the 1 minute mark. So hopefully, please don't pass out. Hopefully you're on your gone past the 1 minute mark. So if you're doing this in teams of 4, you're on the third person, or maybe the first person if you're in pairs is taking over again. 2 other things: please don't blow too hard because the water will go everywhere. And secondly, don't suck. Just remember to blow out. We have had a few little incidents in the past. So just on the live feed, we've got in Kenya, the water is pH 6. Fantastic. We'll find out if there are any other pHs. We're doing super amazing. So predictions also coming through. So with this added carbon dioxide, what is going to happen to the pH of our water? Remembering it was 7.02 when we started. What might happen? Is it going to go up or down that pH, that measure of acidity? 2 minutes. Amazing. Thank you so much.
Here we go. Hopefully I have lots of carbon dioxide in my breath.
Well, we're about to find out. So remembering that when something becomes more acidic, the pH goes down. So we're just going to take this off here. And I wonder what people think will have happened to the pH of this water. Any predictions coming through on the live chat? There we go. So, currently blowing bubbles at Chiltern Edge School in the UK. Absolutely fantastic. We'll see how your experience of this is matching up with ours. So I'm going to put the pH meter in the acidified water. And we're going to see whether the pH has changed. I'm going to keep this secret for now. I just want to sort of ask people what they think may have happened to the pH in this sample. Blowing bubbles at Lamberhurst, great. I wonder who else is blowing bubbles. So I'm going to reveal this. We've got an amazing job by Ellie, and we have, after 2 minutes of blowing bubbles, we have become more acidic. We have dropped our pH to 6.5. So that just shows very briefly this idea, this process of ocean acidification. And as a metaphor, I suppose that through the increased carbon dioxide in the atmosphere, we are blowing bubbles into the ocean and causing the pH of the ocean to drop. But why does that matter? And this brings us to the second half of our demonstration. And what we'll do is some students achieved, sorry, I just got distracted here. In Kenya, we have blown bubbles, and some students have achieved a drop to pH 5. Ellie, pH 5, 6.5 here, pH 5 in Kenya. It's absolutely fantastic.
Good
Well
job,
done.
guys.
Good job. Let's put this down and then turn this off. I'm going to put this to one side. So what we're going to look at now, why does this drop in pH? Why does it matter to some of the communities living in the ocean? I'm going to take, in fact, I might just show, we'll get the pH meter back on and we'll talk about this vinegar. It's going to smell like a chip shop in here very soon. So we have vinegar, commonly available acidic substance, and we're just going to use that because it reacts quite nicely and shows what very speeded up process, exaggerated process of what might happen to some of the life in the ocean. So let's put the pH probe in here and have a little look. And we are down to 2.5, 2.44, 2.4, around there. So this seeing that much more than the oceans are predicted to get to, much more than we have achieved through blowing through water. And take the pH probe out and put it back in the buffering solution. I might rinse it before I do that. I don't have too much vinegar in here. And there we go. Turn this off and come back to our vinegar. So an overly and exaggerated acidic ocean and a very odd looking sea creature, a stick of chalk. Now, ocean acidification, this change in ocean chemistry, affects sea creatures in different ways. And we're going to talk mainly about those sea creatures that have a calcium carbonate structural skeleton. Calcium carbonate, the same mineral as chalk, and shellfish, for instance, will take calcium carbonate from the ocean and use that to form their shells. Coral, hard tropical reef coral will use calcium carbonate in the water and grow their amazing structures. Now, what a change in acidity means is that there are fewer carbonate ions available, so fewer of these building blocks available for shells, for coral to grow. And because there are fewer building blocks available, it makes life far more difficult for the coral animal and for shellfish. I'm just going to put some of this chalk in this beaker. And the reason why I'm breaking it is because very cleverly, chalk manufacturers in this modern day and age coat the outside of the chalk so that it doesn't come off on teachers' fingers or anybody else's fingers. So I'm just going to break it up a little bit. And if I hold this up to the camera, I don't know, Ellie, can you get a zoom in on that so you can see the reaction taking place? And what we can see here is a chalk reacting with the acid. What we're not talking about at the moment is necessarily organisms dissolving into the ocean. What we are talking about is life becoming tougher for a variety of different animals. So if you have to use more energy, if you're a clam just out here in the Arctic Ocean, and you have to use more energy because the building blocks you use for your shell are more scarce, you have less energy for other things such as growth and such as reproduction. So what we can start to talk about is that ocean acidification can have a negative impact on some types of life in the ocean, because in order to make up for its effect, its change in ocean chemistry, they're using more energy. If they're using more energy to make up for this change in chemistry, then they've got less energy available for growing and for reproduction. That means that in the future, animals that have a calcium carbonate structure or a skeleton, they might be smaller and there might be fewer of them. Now, some of you might be thinking, well, okay, it doesn't really matter too much if there are a few chalky, creepy crawlies and creatures in the ocean that, might be a bit smaller, or there might be a few less of them. What we really care about up in the Arctic are those wonderful, charismatic, big animals like the polar bear, like the beluga whale. But it's important to remember that those big, charismatic animals rely on a food chain. So if the tiny wee animals at the bottom of the food chain are getting smaller and there are fewer of them, then that's going to have a ripple effect all the way up the food chain. So what we're looking at the moment, just by blowing through some water and putting a little bit of chalk in some vinegar, is what could take place in the Arctic insofar as that ocean acidification, the change in ocean chemistry, can affect smaller animals at the bottom of the food chain, and that can have a ripple effect on the entire Arctic ecosystem. And the science that we're doing up here is looking at just that. How is ocean acidification going to affect those animals that have a calcium carbonate, or that calcify, to use the science term, calcium carbonate structure or skeleton, and are they being affected, and how might they be affected in the future? So I hope you've all been able to follow this demonstration, this little investigation at school, that you've had fun bubbling through your water, and that you've observed the changes that are happening. We might come back to how our chalk's behaving with the vinegar towards the end of the session. But what I'm going to put these down here, I'll put some lids carefully on them so they don't spill. But really looking forward now to having a look at some of the questions you've sent through, and great to see that at Lamberhurst you've got your cabbage indicator going. Now I hope whoever made that cabbage indicator, very, very easy to do, chopping up red cabbage, boiling it up and straining the water off. It can be a bit whiffy, so best to do with the windows open. So I hope whoever made that didn't stink out of their house too much. But great to see that you are seeing those changes in acidity, those changes in pH, and you're able to get an understanding of the processes that are happening up here. Just to reiterate, we're not talking about the Arctic Ocean changing into a very strong acid, something that's dissolving shells willy-nilly at the moment. But what we're talking about is that pressure being put on those animals, those clams, and other animals that have calcifying behaviour, that have a calcium carbonate structure or skeleton. So over now to some of the questions we've had submitted in advance, and then we'll also be picking up on the live chat questions as well. So I think we're starting. I'm just going to sort of move the pH meter out of the way so I don't knock that. Here we are. So we're starting with Mr. Chris Hunt at Aurea School in Didcot. Great to have you here. Miss Kelly from the 5th High School in Athens, and Miss Deglian, sorry about this, it's a wonderful name, Diluci Anidis from the Anatolia College in Thessaloniki. Welcome. Questions first from the 5th High School. One, are the waters in the Arctic more susceptible to ocean acidification compared to the rest of the oceans, and why? That's an excellent question, and it's one of the reasons why we're studying ocean acidification here in the Arctic. Carbon dioxide dissolves much more readily into colder waters than warmer waters. So here in the Arctic, we're seeing the effects of ocean acidification much faster. I mean, we're actually seeing that the ocean chemistry is changing faster now than any other point in the past 300 million years. And here in the Arctic, those changes are happening even faster. So the Arctic acts a bit like an early warning system. And that's the reason why we're up here. If you want to get an understanding of this, how gases dissolve at different temperatures, differently at different temperatures, all you have to do is observe some very everyday things at home or in the classroom. The first of which is if you have a warm fizzy drink, that's going to go a bit flat as it warms up. It's going to be fizzier when it's colder and flatter when it's warmer as that gas comes out of the drink. The second one is if you're boiling a pot of water. Before it boils, before that steam forms, what you can observe at the bottom of those tiny little bubbles on the bottom of the saucepan, and that as the water gets warmer, those are the gases coming out of solution. So yes, ocean acidification happening faster here. And the second question we're going to take from the 5th High School: what could be done to reverse ocean acidification besides reducing carbon dioxide emissions? A really, really good question. And I think what you're referring to here is something called geoengineering, where we try to come up with a technical solution to some of these big changes being caused by human activity. And one of the ideas for sort of mitigating or trying to change the effects or reverse the effects of ocean acidification is to use iron, to dump a whole load of iron in the ocean. And the reason behind that is iron is one of the nutrients that will drive an algae bloom, so a whole vast area of algae growing in the ocean. And as a plant, that's going to take up carbon dioxide and have that as a sort of sink, a carbon sink, so take that away from it getting into the ocean waters. So that's the idea. It has a number of potential unintended consequences, and it's never worked at scale. So the geoengineering solution that's being put forward hasn't been shown to work at the scale of the problem that we're facing. So I'm afraid to say, or not afraid to say, but we need to be working at the source of the problem, and that is increased carbon emissions. And so everything that we can do to work on reducing the amount of carbon we emit is going to slow the increase in ocean acidification. Reversing may not be possible, but slowing, something we should be definitely working towards. I'm now going to take a couple of questions from Anatolia College. How is ocean acidification affecting me? That's a really good question. And these science topics can seem to be very far removed from everyday life. Now, ocean acidification can affect us in a number of ways. And I talked a little bit about the food chain here in the Arctic. And that's important to remember, that we do rely on the ocean for a lot of things. 1 billion people rely on the ocean for their primary source of protein. A lot of coastal areas are protected by reefs. And if you have a community that is reliant on fishing or on tourism in the oceans and seeing the abundance of life, if you have ocean acidification that's starting to have an impact on those communities, those animals and plants that live in the ocean, then you're going to have that knock-on impact through the food chain up to fish, for fisheries, and also having less abundance overall, potentially, for tourists to have a look at. So we do rely on the ocean, and ocean acidification can start to drive those changes that would have a negative impact on humans as well. Just to say that we're talking about ocean acidification as if it is something that negatively affects every single type of marine life. There are studies showing that some forms of marine life benefit from a decrease in pH, from an increase in acidity. So there's going to be winners and losers, but there is definitely going to be change. And then second question from Anatolia College: what can I personally do to stop it? Now, it's a great question, and I'm not sure which student asked that, but I think that we all have a general idea about how we can start to reduce carbon emissions. We talked a little bit about this in some of the live broadcasts yesterday. And, you might have personal favorites, but very simply things like eating less meat, getting on your bike, remembering to turn off the plug and not to leave things sort of plugged in, and reducing your personal use of electricity. All those things will help to combat and tackle the increase in ocean acidification. Here we are. Questions from Aurea School in Didcot. Some great questions here. Where do you live when you study the ocean? That's a really interesting question. So the science team here are from the University of Exeter, so they have easy access to the sea down there. That's a town in the southwest of England. Up here we're using a research station, and you have a number of research stations around the world, and you have ones that are close to the environments that you're studying. So as a scientist, you might travel to these different places, and you might be here for 2, 3, 4, even sort of 6 or more weeks, and that they're close to the ocean, and you can come and get your samples and study it, and then take all those samples back to your laboratory and do some additional analysis there. So when marine scientists are studying the ocean, often you'll find that they're using a research centre, a field research centre or station, and that allows them to work next to or near the ocean for a number of weeks at a time. We've got bedrooms here, we've got lab space here, sitting room, a little area for making cups of tea to help us through the cold weather, and the luxury of hot showers in the Arctic. So that's fantastic. And a second question from Aurea School in Didcot. We have what aquatic life do you see on a daily basis? Really good question. We see a lot of what looks like slime. So we have, when we're trawling for plastics, we're picking up a lot of algae in the nets. and that looks quite slimy, so that's the life we see. That's probably not what you're asking about. We've got some amazing seabirds out here: eider duck, little auks, fulmars, gulls. A walrus was spotted from the survey vessel yesterday, from the little vessel that we're using for our sampling. We've seen a seal. We haven't yet seen the sea bear, the polar bear, up here yet, but also picked up a couple of great spider crabs from the pier just down in the harbour. So those are being looked at to see whether they've eaten any plastics as well. So a range of aquatic life, but we haven't yet seen the whales come in. Maybe it's going to take a few more weeks for that to happen. So fingers crossed we might look out and see a beluga whale out on the fjord, but not quite yet. I'm just going to take a couple of questions from the live chat, and then we'll come back to the pre-submitted questions. Here we have, great, here we have, how will ocean acidity vary according to your location? As I said before, the change in ocean chemistry and ocean acidification is happening here faster than it is in other places because of the colder waters. And that was a question through, I'm not sure the name of the school, but the username, the Gun Nut. We have, here we are, from Maddie at Lamberhurst. How hard is it to find out how much acid is in the whole ocean? So that's a very good question. So how many samples do you need to take in order to make this claim about, well, the pH of the ocean is this amount here or this amount somewhere else? It's going to change near shore because you've got that fresher water, that water that's nearer pH 7 coming from rivers. So we've got a fresher water out in the fjord here with that glacial runoff. So you're going to have all these differences in pH and seasonal differences as well when you have the plankton, the algae growing and taking up some of the carbon dioxide. So you've got all these changes around the planet, different times of year, different sources of water changing and mixing the whole time. And we rely on scientists taking samples of water and testing the pH. That's one of the things that we're doing here. We're taking samples of the water and we're testing its pH so that we have a record of what the pH of the ocean is here. And scientists worldwide are doing the same thing, sharing that information and making it available, so we have this idea of what the pH is, the acidity is of the ocean around the world. And lots of questions coming through from Chiltern Edge in the UK. Oliver, how cold is it today and how cold is it at night? Great questions, Oliver. Oliver, it's really warm today. So I think it is about 2 degrees, 3 degrees, which is seriously warm for this part of the world. That's mid-30s Fahrenheit. And talking about night, we don't have night at the moment. We have 24 hours of daylight, and so you don't really get that change too much of temperature between night and day. If it changes depending on how temperature changes from day to day and the wind and everything else, but not really between night and day. Although it was blowing an absolute hoolie, that technical term for a strong wind last night with a lot of blowing snow. So really warm at the moment. I have been up here, well, last year when I was up in Neolson, we had one day when with wind chill the temperature was down to I think -53 Celsius, which if I can quickly work that out in Fahrenheit is about -65, -70. So that was a bit nippy. But this year it's been very warm. I think probably what's happened is that spring has come early, and we're in the week where we're changing from the winter to the summer, very short spring here. And so we have this very warm weather and rain this morning. So feels a little bit unarctic, but it is 2 degrees and raining. One more question from Chiltern Edge. So, Luke, does ocean acidification affect the coral reef? Luke, yes it does, and it does in the way that I was talking about earlier, insofar as corals are finding it harder to get the calcium carbonate, the mineral they need to grow their structure. And so that means that there can be less energy for other processes, so growing and reproducing as well. So a really good question there. So back just to make sure we get to the pre-submitted questions. We're back to Athens. And in fact, what could be the consequences of ocean acidification for coral reefs? So the 5th high school just talked about that just now. From Thessaloniki, in terms of reversing ocean acidification, I think what we should be really looking at, as mentioned before, is trying to slow ocean acidification. I think reversing it will, may not be possible in the time span that we're going to be around for. And then coming to Aurea School in Didcot, lots of great questions here. What is the biggest mammal you have seen in the ocean? I've had the great privilege of seeing humpback whales down in Antarctica, but not, we haven't seen a blue whale. Apparently you do get blue whales into the fjord here, so the biggest creature that has ever lived on planet Earth might be through this door. Probably a bit later in the season, so there's actually a snowdrift in the way if I open this door. But if I poke my head out, I can't see any whales at the fjord. But I'll go and have a look after lunch. Great question here. Why are some parts of the ocean warm, whereas some parts are cold? A lot of factors from that, all the way from warming from solar energy and the ocean currents taking warm water, for instance, from the Caribbean up through the Atlantic past the UK. So there's a variety of reasons, and it's a great little demonstration we can share with your teacher, which is about thermohaline circulation. So how different temperatures of water and different saltiness of waters can affect ocean circulation, and how that brings nice Caribbean water to the UK and keeps us warm. Now, this is something that I will need our wonderful classes to come up with and find an answer and calculation. Here's a little challenge for you. This is a question from Aurea School. How many litres of water are there in the ocean? I have no idea. That there is a maths conundrum for you guys to calculate how many litres of water in the ocean. So let's get some answers to that coming up on the live chat. Wow. And then what do you find on the ocean floor? It really depends where you're looking. Some colleagues, friends of mine, are looking at the ocean floor using submersibles, and that's the Necton expeditions and Necton missions, and they're finding a variety of things on the ocean floor. They've just published, if you're in the UK, if you go to the Daily Telegraph site this morning or this afternoon, you'll find that they found 100 new species on some seamounts off Bermuda. So lots of new things to be discovered on the ocean floor. And lastly, why did you decide to become a marine biologist or chemist? Really great question. I have the great privilege to work with a variety of marine scientists. To tell you a secret, I actually studied history at university and then changed to doing more science communications and education work later in life when I joined marine scientists up in the Arctic 7 years ago. So I find it absolutely fascinating. I think it's something I would have liked to have studied more when I was younger. But the ocean is like an unexplored world, and we think about the new frontier of exploration being space, going to Mars, going to other planets, whereas there are so many areas of our ocean that are unexplored. And just a 6-week expedition on some seamounts off Bermuda, which are quite regularly visited, yielded 100 species new to science. So that's really exciting. So many things to explore. So do look at the ocean more and do think about following science as a career. We are nearing the end of our live chat, live broadcast today, and there are a lot of questions that have been coming through. And I'm sorry I haven't got to all of them. Ted at Brookhouse, Rwanda in Kenya, what is the main source of electricity for you guys here? We use a diesel power station, to be very honest, because it's the most secure form of power where we are. Solar power in the Arctic, tricky. Wind power, also tricky because of the strong winds that come through. So ironically, in an area that is being most affected by the use of fossil fuels, it is really one of the only options that we have. So please do think about more sustainable forms of electricity where you are, where it's more feasible. What did you eat for breakfast? Bowl of cereal, cup of coffee. I'm going to whip through these now. Session at school just ended. Thank you so much to Greece. Thank you also to Athens. Switched some classes too. So I think we've, that was from Ferndown Upper School, eating for breakfast. I'm just going to check back. Hardest part of your stay in the Arctic from Jack at Chiltern Edge, being away from loved ones, from my family, from my wife and children. Very much looking forward to seeing them this weekend. Susan Blomley, do you think sea creatures will adapt to a more acidic environment? We will see. I hope so. I hope so. It all depends on the rate of change. So when we're looking at these changes in environment, adaptation can take a long time. So if we can slow down the rate of change, then there is more chance for life to adapt to that difference. And just making sure, Morgan at Lamberhurst, does acid make animals die? Yes, if it's the kind of acid that I used this morning. If we're talking about what's in the ocean at the moment, it can cause stress and pressure on life in the oceans, and not necessarily delivering that sort of fatal blow that you may be thinking about. We're not putting animals in acid baths that you might sort of think of from a horror film or something. That looks like we've managed to answer most of your questions. Thank you so much. It's been a really great session with you today. Thank you for tuning in to XL Catlin Arctic Live. We've got a great range of talks still to come today. I'm delighted to have Dr. Katie Smith joining me in an hour's time. We then have an open question and answer, so if there are additional questions that I haven't got through from your students, please post them then. We're then changing our times to suit the American market, so our viewers and schools in North America will be able to tune in from their morning or afternoon for a second ocean acidification live investigation, another interview with Dr. Katie Smith, and an open Q&A to round off the day, 8 o'clock our time, and that's 3 p.m. Eastern time and noon Pacific time in the USA. So thank you very much for joining us. For now, it's goodbye from the Arctic.